March 1945, Bielefeld, in the North German state of North Rhine-Westphalia. A grey morning, the kind that never really gets light. A German railway engineer picks his way across broken ballast toward what used to be a viaduct, carrying trains south toward the Ruhr. He has inspected bomb damage before. Plenty of it. He knows what a direct hit looks like. A crater punched into the top of a structure, concrete thrown outward, twisted rail hanging in the air. He has seen that picture 100 times in 4 years of war. This is not that picture. 2 of the great brick arches supporting the viaduct have simply vanished. Not cracked, not chipped. Gone, as if some enormous hand had reached up from underneath and pulled the ground out from beneath them. There is a crater, but it is nowhere near the viaduct itself. It sits in the soft earth beside the piers, deep and narrow, more like a well than a bomb crater. He walks to the edge of it and looks down and cannot see the bottom. No aircraft had been seen diving on the target. No formation had circled to correct its aim. A handful of bombers had come over, high and fast, dropped what looked from the ground like a single item each, and left. And now a structure built from 100,000 tons of masonry, standing for 80 years, was lying in a heap in a river valley, brought down by something that had not even touched it. He kneels by the strange, narrow crater and tries to work out what could have done this. He is trained as an engineer. He understands stress, load, the way weight travels down through an arch into its foundations. Nothing in his training explains a bomb that appears to have missed the target and destroyed it anyway. This is not a story about a bomb that hit hard. Plenty of bombs hit hard. This is a story about a bomb that was never meant to hit its target at all, and about the strange, patient, almost geological idea that made it work. An idea so far outside what German engineers believed a bomb could do that when they finally understood it, some of them refused to believe the numbers in front of them. If you like stories about the quiet engineering arguments that decided the war behind the more famous battles, stick around, because this one runs deep, literally. To understand why a German engineer could stand at the edge of that crater and not understand what he was looking at, you first have to understand what a bomb was supposed to do and what German concrete had been built to survive. By 1944, both sides in this war had settled into a comfortable mutual understanding of how bombs worked. A bomb was a container of high explosive with a thin steel case, built to shatter on impact and release its blast outward in every direction at once. The case existed mainly to hold the explosive together on the way down. The thinner it was, the more of the bomb's weight could be given over to explosive filling, and the bigger the bang for the size of aircraft carrying it. This was, and remains, sound thinking. A blast bomb is an efficient way to destroy things that are not especially well protected. Houses, factories, railway yards, soft-skinned vehicles. Germany had built an enormous amount of infrastructure on the assumption that this was the only kind of bomb it would ever face. Submarine pens at Saint-Nazaire, at Lorient, at Brest, roofed in reinforced concrete 7, 8, in places closer to 9 feet thick. Later, purpose-built assembly halls for the V-weapon program, buried under concrete domes designed from the outset to shrug off direct hits from the heaviest bombs the Allies were known to carry. The doctrine behind all of this was simple, and it was not foolish. If a bomb detonates on the surface of a structure, or a few feet into it, the roof needs to be thick enough that the blast cannot punch all the way through. Build the roof thick enough, and the bomb becomes irrelevant. Every calculation German structural engineers made assumed the explosion would happen at, or very near, the point of impact. They had good reason to believe this. Every bomb ever dropped on them up to that point had behaved exactly this way. A thin-cased bomb hitting reinforced concrete at a few hundred miles an hour does not go far. It slows almost instantly, crushes, and detonates within inches or feet of the surface. The roof absorbs the shock. The pen survives. German engineers had watched this play out again and again, at Saint-Nazaire in particular, where thousands of tons of Allied bombs had fallen on the pens across 3 years of war and left barely a scratch on the structures they were built to protect. By 1943, this was not a hope. It was proven fact, backed by years of direct evidence, and the men who had built those roofs had every right to trust it. There was a second layer to their confidence, and it is worth taking seriously because it is the same confidence every engineer in this story will turn out to share. on both sides, until events overtake it. German industry understood, correctly, that a bomb's ability to penetrate before exploding was governed by simple physics: mass, shape, and the strength of the case against the resistance of whatever it struck. A thin-cased bomb, however heavy, deforms and detonates almost on contact, because its shell cannot survive the deceleration forces involved in punching through solid material. To go deeper, you would need a bomb case strong enough to survive an impact, violent enough to destroy almost anything else it touched, while somehow keeping enough of its weight free for a useful quantity of explosive. German ordnance designers had looked at that problem, worked through the metallurgy, and concluded it was not worth pursuing. The gains would be marginal. The engineering cost would be enormous. Better to build thicker roofs than chase a bomb design that seemed to fight its own physics at every step. Here is the part that deserves to be said plainly, because it is easy, looking back, to make the Germans sound slow. They were not slow. Every calculation they made was correct for the bombs that existed. Their roofs really did defeat every bomb the Allies had. Their reasoning about penetration and case strength was sound engineering, not guesswork. They had simply never met the man in a drawing office outside London who did not believe the problem was worth avoiding at all, because he did not believe the bomb needed to go through the roof in the first place. His name was Barnes Wallis, and to understand what he built, you first have to understand the idea that nobody around him initially wanted to hear. Barnes Wallis was, by the outbreak of war, already an unusual figure inside British aircraft engineering. He had made his name designing airships, including the enormous R-100, at a time when most of his colleagues considered lighter-than-air flight a dead end. He thought in structures the way other men thought in sentences, instinctively, and he had a habit that made him difficult to work with. He kept asking questions other engineers considered already settled. Early in the war, Wallis became fixated on a specific problem. Bomber Command's aircraft, by the standards of the day, could carry meaningful weight. But every bomb dropped from them, however large, behaved the same way against a hardened target. It hit, it crushed, it detonated at or near the surface, and a thick enough roof simply absorbed the blow. Wallis looked at that pattern and asked a question almost nobody else in British ordnance design was asking in 1941. What if the bomb was never meant to hit the target directly at all? His reasoning, laid out in a paper he circulated privately that year, was almost geological in its logic. Structures like viaducts, dams, and reinforced bunkers do not float in space. They sit on the ground, and the ground itself provides much of their stability. If a bomb could be made heavy enough and shaped correctly enough to punch not through the target but past it, into the earth beside or beneath the foundations, and detonate there, deep underground, the explosion would not need to overcome the target's armor at all. It would simply carve a vast cavity out of the earth supporting it. The structure would lose the ground it stood on, and it would come down under its own weight, the way a bridge collapses when the riverbank beneath one of its piers washes away. This is what came to be called the earthquake bomb, and the name is more literal than it sounds. Wallis was not proposing a bigger bang. He was proposing to use the bomb's mass and speed to turn a portion of the earth itself into the weapon, transmitting a shockwave through solid ground that no roof, however thick, could do anything to stop, because the roof was never in the blast's path at all. The idea sat largely unbuilt for 2 years, partly because Wallis was consumed with the far more famous bouncing bomb project that would be used against the Ruhr dams in 1943, and partly because a bomb heavy enough to do what he described did not yet exist, and neither did an aircraft capable of lifting it. But the dams raid proved something important about Wallis that mattered enormously to what came next. It proved that when he said an apparently impossible idea would work, it was worth someone finding out whether he was right. By 1943, work began in earnest on turning the earthquake bomb from a paper theory into hardware. And here, the engineering problem the Germans had already dismissed as not worth solving became the entire project. To reach the depth Wallis needed before detonating, the bomb had to survive an impact that would destroy almost anything else. That meant abandoning the thin-cased design every existing bomb used and building something closer to an artillery shell the size of a small car. A single piece of high-grade steel, cast and forged as one continuous shape rather than assembled from separate plates, thick enough to survive supersonic impact with the ground without shattering, buckling, or detonating prematurely from the shock of its own arrival. The result, entering service in 1944, was called Tallboy. 12,000 pounds in weight, over 5.5 meters long, shaped less like a conventional bomb and more like an elongated